In this assessment, we returned to this molecule here, which was used in a previous assessment. In the previous assessment, we were asked to just give the ratio of the peaks, and we weren't worried about the chemical shift. Here, we're adding to it the chemical shift. In later videos, we will add multiplicity as well. So just as a reminder, if we're going to kind of sketch a spectrum, ignoring splitting patterns, but keeping in mind the chemical shift, let's start with the information we already know. And that is for A, because all three methyl groups are the same, A's signal will integrate to 9 hydrogens. B's signal, because B is a CH2 and they are 2 unique hydrogens, it will integrate to 2. C is also 2 hydrogens, it will integrate to 2. D is only a CH, it integrates to 1. And because there's free rotation around the CD bond, the 2 methyl groups at E are identical, so E will integrate to 6. So when we place these signals, we'll need to make sure that we show those integral values. Now, where should we place each signal? Let's start with A, and we'll go A through E, that seems creative. If you look at the expected chemical shift for A, we've got hydrogens on carbon that aren't directly attached to electronegative atoms. There's no resonance, there are no neighboring double bonds for us to worry about. So these would be considered just normal aliphatic hydrogens, hydrogens attached to sp3 hybridized carbon with nothing that's particularly electron withdrawing or electron donating nearby. And so for those, maybe because of the slight proximity, we'll say that these would be around 1.1. Now again, we're using that approximate value, approximately 1.1 parts per million. Could it be 0.9? Sure. 1.3? Sure. But we're just going to put it around 1.1. We certainly wouldn't want to put it higher than 2 because that would suggest it's neighboring something electronegative, double bond, etc. B, on the other hand, is a hydrogen on a carbon directly attached to an electronegative atom. For that, we'll say that we expect that one to show up between 3 and 4. If we're going to sketch the spectrum, we want to give a single number. So we'll say that this is going to be around 3.3 parts per million. If we jump over to C, the description of C would be the same. It's 2 hydrogens on a carbon attached to an electronegative oxygen. So probably it's going to be right around 3.3. Just so we can give it some space, we'll put it around 3.5. Again, 3.3, 3.5, 3.2, but we have to put it somewhere. So we'll try to have it look like it's around 3.5. And when we get over here to draw, there might not even be the resolution on the screen, but we'll put it somewhere between 3 and 4. When we look at D, it's 1 hydrogen on a carbon that is not directly attached to an electronegative atom. We'll say that it's around 1.3. Again, just to differentiate it between the one at 1.1 so that we can show it on the screen. And then the 2 hydrogens, or the 6 hydrogens that represent E, once again, hydrogens attached to carbon, we'll put those around 0.9. And I can already imagine when you look at our picture over here, our spectrum, it's going to be really tough to squeeze all of these in. We'll do our best. This is what really matters, though, is knowing the integral value and what chemical shift. Well, how we draw it, well, we're not great artists, but let's see what we do. So we're going to have something around 0.9. So we'll start our line about here, and we'll start coming over. We get to 1.9, and we'll go up like so. So there we go. There's our peak at 0.9. So we wanted to have one at 1.1 that's going to be a little bigger because it's 9 hydrogens. So we'll draw sharply higher signal there. That's at 1.1. For D, signal D, we're going to be around 1.3. So maybe we come a little bit farther over here. This is about 1.3, but it's going to be a smaller peak because it's going to only integrate to 1. And we'll assign integral values later. Now we're going to go all the way past 2, past 3 to around 3.3. We've got 2 hydrogens, so a little bit taller than the 1 hydrogen, then over to 3.5, a little bit same height as that. And then we would keep going. Let's see if I can stop. A little too far. There we go. So it would look something like that. Now we should go ahead and label the peaks 2 different ways. Let's label them as A, B, C, and D just to make sure that we're all on the same page. So we said that this one was E, the one at 1.1 was A, the one at 1.3 was D, 3.3 was B, and 3.5 was C. Now, I've drawn these peaks to kind of, the signals to kind of represent the relative integral values, but let's go ahead and label those integral values just so there's no confusion. This one will integrate to 6, A integrates to 9, D integrates to 1, C integrates to 2, and B also integrates to 2. Again, that labeling is really just to make sure we're all on the same page in case our art doesn't show it exactly the way we want it to. We'll revisit this same assessment, but add in multiplicity, showing whether these are doublets, triplets, singlets, etc. Stay tuned for that one.